So now that we have all the protons and carbons in the furan ring and off to the side assigned, we want to find our way into this second ring in the molecule. And basically we have defined some kind of handle in. We have to take something we already know and we have to use that to find our way into this secondary ring. So the way I'm going to do that is I am going to use this proton on carbon 5. I'm going to use that to see, can I see any long-range couplings in the HMBC over to this ring? So can I see a 3J coupling? Remember, this is only 3 bonds. So 1, 2, 3 bonds from carbon 18. It's also 3 bonds from carbon 14. So can I see a coupling from the proton on carbon 5 into this ring somewhere in the HMBC? So let's go down to the HMBC and see what we can find. So looking down here in the HMBC, I want to look at everything that proton number 5 here can see. And we can see that it does have a couple of cross peaks down here to a couple of carbons that we haven't identified yet. There's one here at 140.75 and one here at 154.57. But I haven't assigned any of these carbons in this ring yet. None of these 4 have been assigned, so I don't know which one is which. However, there's very little chance that the proton on carbon 5 can see all the way to 17. That would be a 1, 2, 3, 4 bond coupling, which isn't impossible in systems like this, especially with pi conjugation in the mix, but it's pretty unlikely. So it does see something here at 140 and something here at 154. So let's go into the HSQC, because if one of those is proton number 18, or if one of those is carbon number 18, it should have a proton on it. And we can use that to find proton in carbon 18, because I'm unlikely with proton number 5 to see any other protonated carbons that I haven't yet assigned. So let's go into the QC and investigate carbon number 140, and yeah, there's a cross peak at 140 ppm down here. And again, that's the only reasonable choice for that signal is number 18 right here, because that's the only one that's likely going to be observable by number 5. So I'm going to go to manual assignment. I'm going to click at the center of that peak, and I'm going to click on protons in carbon 18, and you can see MNOVA's now got those assigned. So I could go digging into a COSY to figure out, oh, well, what is proton and carbon number 17 then? Well, I could go into the COSY and figure that out definitively, but also I only have 1 proton signal left that I haven't assigned yet. I still would have to assign carbons 16 and 14, but there are no protons on those carbons. So the only proton signal I have left to assign is number 17, and if we look, ignoring water and DMSO, I only have 1 actual proton signal left. It's a doublet. It's not been assigned yet. So I have to know just by process of elimination for sure that that is proton and carbon number 17. So I can scroll down here and I can do a manual assignment again to click in the center of that peak and assign that as number 17. And there it is. We've assigned every proton in the spectrum, and we just now need to pin down these last couple of carbons. So how do I go about doing that when I don't have any protons on those carbons to be able to find and then use the HSQC to pin down carbons 16 and 14? Well, my only option is to go to the HMBC spectrum and look for correlations there. But here's the trick, is that both of these carbons, so typically you want to remember that in HMBC spectra, 2 and 3 bond couplings are extremely common. 4 bond couplings are somewhat rare, but not at all unheard of. But they're a little shaky. But 2 and 3 bond couplings are rock solid, show up every time. Now, Typically, 3 bonds are counterintuitively a little stronger than 2 bond couplings. The Karplus equation typically explains that. So you can sometimes make inferences based on the size of the cross peak, but I would treat that as a very last resort. So I want to find a more definitive way of pinning down which signal is which here. So if I remember that 2 and 3 bond couplings are very common in the HMBC, I can't really use carbon-16 to tell the difference between protons 17, 18. I can't use those to find 16 because proton number 17 is 1, 2 bonds away from 16. Proton 18 is going to be 1, 2, 3 bonds away. I would expect both of those to couple with carbon number 16. So what you want to do is you want to set up some kind of test whenever you're in a position like this and you have a couple of signals that are ambiguous, that you're not quite sure which one is which. You want to set up a test so that one of your signals that you know, one of your protons that you know, can pass or fail that test so that you can then identify the ambiguous peak. So in this case, 17 and 18, those protons are each within 3 bonds of carbon number 16. So I can't really use them to find carbon number 16. However, I can use them to find carbon number 14. So the carbonyl carbon, we would typically guess that the most downfield carbon in the spectrum is probably the carbonyl, but that's not a guarantee. I want to be very sure about that. So can I use 17 and 18 to tell the difference? And in this case, I can, because proton number 17 is going to be 1, 2, 3, 4 bonds away from carbon number 14. Proton 18 is only going to be 1, 2, 3 bonds away. So I can very reliably expect proton 18 to couple to carbon 14, but I would not expect proton 17 to couple to carbon 14. They're on opposite sides of the ring. It would be pretty unlikely for them to couple to each other. So I want to go look at the couplings of proton 18 and see, is there a carbon that it couples to that proton 17 does not? So to do that, we're going to zoom into this region of the spectrum. Remember, these are the last 2 carbon peaks. These ones at 154 and 165. These are the last carbon peaks we haven't assigned. So I want to look for what is a peak in here that proton 18 sees. What is a carbon in here that proton 18 sees that proton 17 does not? So we see 17 is over here and 18 is here. So what do they see? And we can see that they both see this carbon at about 165, 166 ppm. They both have a cross peak to that. However, only carbon 18 has a cross peak to this signal at 154 ppm. And again, we would expect both of them to couple to carbon 16. We would expect only 18 to couple to carbon 14. So that tells me really, really definitively that carbon number 14 is the signal at 154 ppm, and then carbon 16 is the signal at 165 ppm. And that's not necessarily intuitive. You can often make an assumption that carbonyls are going to be the most downfield peaks in your carbon spectrum. However, had we made that assumption in this case, we actually would have been wrong. Again, if you remember the discussion of why are the protons on this nitrogen here, why are they 2 diastereotopic 1H singlets? And it's because there's a lot of double bond character on carbon in the bond from carbon 16 to nitrogen here. So the electronic environment of that is not necessarily going to be what you expect. But given what the HMBC has told us, we can now very confidently assign the carbon at 154 was the one that both of our protons saw. So we can, just to double check, we can go back to the HMBC and we can see that yes, they both have a cross peak. Excuse me, the carbon at 165 is the one that they both saw. The one at 154 is the one that only 18 saw. Therefore, we can know very confidently that the signal at 154 ppm is going to be our carbonyl carbon, and our signal at 165 is the last unassigned peak in the spectrum, carbon 16, which is the quaternary carbon bonded to carbon 17 and the two nitrogens. And with that, we have fully assigned and characterized gemcitabine. That is the process for going through step by step, assigning all these peaks, figuring out which proton and carbon are which, and I hope you found all of this helpful.